Hello everyone, this is Patrick from Security and Privacy Academy. Today we are talking about RSA encryption, so let's jump into it. This is going to be a video with basically just only equations, and I'll try to make it as understandable as possible. First, we choose two large prime numbers, p and q. We multiply them to get n. Afterwards, we calculate psi of n as p minus 1 times q minus 1. Next, we choose a number e, which is greater than 1 and smaller than psi of n. E has also to be relatively prime to psi of n. This means that if, for example, psi of n is 72, e cannot be 2 or 9, since both numbers are dividers of 72. Also, e cannot be 70 or 63, since both numbers share dividers with 72. For example, 2 and 9 respectively. When we have our e, we then calculate a d such that e times d equals 1 mod psi of n. How can we achieve that? Let's again look at our example with psi of n equals 72. If we choose an e equals 5, we can try all numbers until we reach a d equals 29. As you can see, 5 times 29 equals 145, which is 1 mod 72, because 2 times 72 is 144, which is 1 less than 145. So this concludes the algorithm. NE, the tuple NE, is our public key, and the tuple ND is our private key. To encrypt the message M, we calculate m to the power of e mod n, and to decrypt it, we calculate c, the ciphertext, to the power of d to return to the original message. Now, why does this algorithm work? If p is prime, which it is, we know that there are p minus 1 relatively prime numbers, since all numbers below p are relatively prime to p. If we remember how we constructed psi of n and n, we see that psi of n equals the amount of relatively prime numbers to n, since it is simply the product of the amount of relatively prime numbers to p and q respectively. To illustrate, if we choose p equals 3 and q equals 5, we get an n of 15 and a psi of 8. That means that there are 8 relatively prime numbers to 15, which is indeed correct, as we can see here. Every other number between 1 and 15 shares a divider with 15. As a little intermission, we briefly need to look at the Fermat-Euler theorem, which states that if m and n are relatively prime to each other, then m to the power of psi of n equals 1 mod n. Psi of n is the same function as before. If we do the same with p, which is prime, itself, then we reach Fermat's little theorem, which states that m to the power of p minus 1 equals 1 mod p. We will need this to show how RSA works. Let's start with Fermat's little theorem. If we multiply the exponent by k times q minus 1, we eventually get 1 mod p on the right side, since 1 to the power of anything stays 1. If we now multiply each side with m, we increase the exponent on the left-hand side with 1 and have as a result on the right-hand side m mod p. You will recall p minus 1 times q minus 1 as the construction we used for psi of n. Therefore, we can simply simplify the equation to this. Everything should be clear so far. Now the magic happens. We have m to the power of 1 plus k times psi of n equals m mod p. Remember how we constructed e and d? It was such that the product equals 1 mod psi of n. If we zoom in on the exponent 1 plus k times psi of n, we see that this is also one mode psi of n. Why? Because the mode does not care about multiplication, so we can ignore k. The only thing that remains is now 1, because any number is just 0 mode itself. This in turn means that m to the power of e times d is again m mode p. Why do we care? Because this is exactly how we encrypt and decrypt the messages using RSA. That concludes today's video. Thanks for watching. Tell me in the comments which topics you would like me to cover, like and subscribe to the channel, and see you in the next video.